while the intuitive approach from the previous video is pretty good, what we're going to do in this video is be extremely pedantic and count the exact number of calls to binary search to make sure we really get what's going on. Now, this is a bit of overkill for this class, but I still think it's important to us to feel good about what we did in the previous video. So what we're going to do in this case is use the number of calls to binary search as our cost model. And we're going to ask ourselves, how many recursive calls get made total, or calls get made total? And so what I've given you here is, let's suppose that n equals 6. That is, if we take the high index and the low index, subtract them and add 1, there are 6 items total being encompassed by the low and high indices. Here I'm showing you the middle, and your job is to figure out how many times are we going to have to repeat this process before we have just one item left in the worst case. So if C is the number of binary search calls, it's how many rows we show here, how many different little pictures we'll show of this array. Give it a shot. Hopefully you come up with an answer you're happy with, and I'll wait for you to figure that out. Okay, so it turns out the correct answer is 3. Okay, why? Well, in the worst case, we end up doing this bigger problem, the size 3 problem, instead of the size 2 problem. If we go to the size 3 problem, then we end up with a middle that's here, and either of these two are the worst case, and in total, we end up with 3 steps, right? 3 total calls to binary search to get down to size 1. So the 3 total calls were n equals 6, n equals 3, and n equals 1, respectively. Great, that's the exact count. Okay, so understanding that's super important for the next step, so make sure that makes sense to you before proceeding. And so let's move on. So as we did before, to understand the runtime, we're going to look for a pattern that relates n and C of n, our cost model. So we already know that if n is 6, the cost is 3, as we just showed. And we're going to fill in this table and try and build up a pattern. So if n is 1, of course, the total number of calls is just 1. We only have one item to look at. In fact, that's this case down here, n equals 1. There are 2 different cases where we end up making 2 total calls. If we have an array of 2 items or an array of 3 items, in the worst case, we're going to end up with 2 total calls right here. We do n equals 2, then n equals 1. Now, once we get up to 4, turns out, once you get up to 4 or 5 or 6 or 7, any of these numbers, if we have that many items in our array, the total number of calls in the worst case will be 3. Now, it could be less. I mean, maybe you get lucky and the item you look at first is the answer. But in the worst case, if you have, say, 6 items, you'll then have to look at an array of size 3, then an array of size 1, and then you're done. And likewise, once you get up to 8 and 9, it turns out that each of these, in the worst case, will end up calling the binary search routine on an array of size 4, and so forth. And you end up with this nice tree structure here. Okay? So in all, we can see that every time we hit a new power of 2, 1, 2, 4, 8, that we increase the amount of work by 1. Okay? So that already feels like log n. Now, we could actually just call it a day there and say, doesn't this clearly look log? But I'm actually going to get even more pedantic. Now, it's going to get just slightly technical, and it's a little silly, but I'm just doing it so we feel really good about what we're doing. But this is pretty much a good enough argument. But if we go a little deeper, we can actually get the exact count and say that it's going to be the floor of log base 2 of n plus 1. Okay? Where did I get this expression? Careful inspection of this pattern. And you can double check my work later if you'd like, but this is an expression that I came up with. There are other very close to this expressions which also work, but that's the one I picked. Okay? So this is the exact number of calls to binary search that you get as a function of n. And so the question then is, well, what's the overall runtime? Well, we can say that since each compare is going to take only constant time, in fact, the amount of work inside of binary search, all of this is just constant work. In fact, let's make that extra clear. We're going to edit the slide live. Ready? Each call takes constant time. Okay, good. All right, I like that better. I have to wait for, so since each call takes constant time, then the overall runtime is going to be the same in order of growth as the overall number of calls. So in this case, I'm going to drop the 1 because that's clearly going to be insignificant for a large n. And so we end up with the overall runtime as big theta of floor of log n. Now, I think that this is too complicated. It looks ugly. And so what we're going to do is simplify it down. And I'm going to rely on a few properties I'm not going to prove, but if you're curious, you can look in the online textbook. There's some exercises. These aren't that hard to prove. So to simplify big theta of log base 2 of n all floored, what we're going to do is note that the floor of f of n grows at the same rate as just f of n. Okay, so the floor of f has the same order of growth as f. It's big theta f of n. That's also true for the ceiling function, by the way. We don't have to use that here, but it's a handy thought. And then actually another really important point is that it doesn't matter what the base of the logarithm is that we choose. If we have a function log base p of n, it grows exactly like log base q of n, and you can show that using just a simple change of base identity. And so again, the online textbook exercises, if you really want to prove these things, they're there. They're not so bad, but I don't want to do it in lecture because it's just a little too much. And so overall, what we can say then is that because the floor of log base 2 of n, if we apply these rules, because it grows exactly like n, we can say it is big theta of log n. Now you'll notice I use equal here instead of the belongs to symbol. I'm just going to use them interchangeably because you're going to see them interchangeably in the world. But basically here, since the base is totally irrelevant, what's interesting is I'm just going to omit it completely. I'm not going to say 2 or 4 or 8 or 6 or whatever. I'm going to leave it blank because it doesn't matter for big theta. And because we generally will have simple expressions inside of the big theta, I'm also going to remove the parentheses around the n because it looks nicer in the big theta. So that's a common thing that you'll see out there with others, right? It's just purely aesthetic, but I like it better. So it's theta log n. Okay, great. So this is what we've got. We had the intuitive argument, but here we've made it better. We have said that we can get the exact count, which is floor of log base 2 of n plus 1, but using those little rules we just saw in the previous slide, that's just theta log n. And, see, now I don't mind, we'll share. There's a lot of work that goes into these slides secretly. They don't just appear from space, and so I at one point was counting compares, but decided to count calls and didn't catch it before I did this recording. But, you know, hey, I'll reveal the secret that things aren't always perfect before I start. So since each call takes, see, now we got to fix this plural. Okay, we'll do it. Ready? I have to wait for the lag. Okay, so since each call takes constant time, that means that the runtime overall will be theta log n. And that's it. We're done. We have found, and now we see binary search. Okay. Well, it's getting a little silly to keep fixing things, but we're friends here, right? Now, is that on other slides? No. Okay, good. Okay. So we're done. We found that binary search is theta log n. But here we can see a third approach, which I'm not going to go through any detail, but you can do this also with recurrence relations, which we saw in our previous recursive problem. You can write out that c of 0 is 0, c of 1 is 1, and c of n is 1 plus c of n minus 1 divided by 2. And it is possible, given this, to show that c of n equals theta log n. That's an alternate approach, but I don't want to talk about solving recurrences in this class. And if you want to, you can go learn about that on your own, but that's it for us in 61B. So the last thing I want to say about this binary search example is that log time algorithms are really, really fast, right? So in practice, it turns out that if you draw up this table here, you'll see that log is actually not really any worse than constant. So even for really, really, really huge data sets, just arrays that are actually bigger than Java will let you make, log base 2 of n, what's a small number? It's 46.5 compared to much smaller arrays, which have 16.6. Like this function grows very, very slowly. And so on a typical computer running on an array of this size, were it possible, to actually build an array that big, would take only 7 nanoseconds to binary search compared to this little dinky array where it takes 1 nanosecond. So log time's really good. I mean, yes, I guess it'd be better if it was 1 nanosecond for everything, but log is excellent. So when you see log, you should feel really good about yourself and what you've achieved.